Hi everyone, this is assignment 3, and my name is Kevin. First, we have to explain figure 37, 38, and 36. First, our process. Where does our process take place? When a massive star already burned out, and each of the cores will become iron, and start to collapse, and then it will suddenly explode only in few seconds, and only in few seconds, this our process takes the time. And then I read bad at chemistry, so most of this topic from the reading. And the rapid neutron will burn add neutron into element until nuclei and cannot hold anymore. The explosion, so the neutron will freely and rapidly collapse each other. And then we talk about each curve has become iron. So the neutron will cut into the iron, and its mass becomes bigger and bigger. Then only the nuclei undergo beta decay, and it can become the next heavier element. So the build-up zone even past the uranium and thorium, then stop only when the nuclei gets bigger than the neutron impact causes them to fusion. And let's talk about S process. Where does the S process take place? Just during the relatively long process of stellar evolution. So all its evolutions will have S process. So each time neutron capture the produced and unstable radiation isotope, the decays occur, change either a neutron into a proton or a proton into a neutron. But not all of the stable isotopes found in solar system matter can be produced in this way, such as this is produced by proton bombardment, and down of this are our process produced by our process. Then this element, so the picture we looked at last week, the element heavier than iron will build by neutron irradiation. Right. And first we talk about S process. Neutrons are spaced out in such a way that nucleus has time to actually stabilize through the beta decay. Thus, the build-up phase follow the build of stability shown in this figure. And for the same reason, it terminates stop at a piecemeal 209, the heaviest stable nuclei, and the top of that stable line. And this should be our process. No sooner has the nuclei absorbed one neutron than it hit by another. No time exists between heat and radiation decay. Instead, radial decay occurs only when the nucleus becomes so neutron rich and cannot absorb any more, as indicated by very tall ash band in the figure. Just a dark gray, the dark gray side, gray side. And this is all.
Okay. Stay here. Group A students, any question, comments? Okay, Ian. Hang on.
I wanna ask that could you please go to the very beginner page and about iron.
Error. Which one?
Page 2 or page 3? Page 3.
Yeah.
And you say when a massive star already burned out and it's program. And I wanna ask that why is B iron or
Sorry, what's the question?
Become iron?
yeah? Why is iron?
Iron. Why?
Why?
Oh. Why? Because the iron is it burn out, it become the most stable element. Is iron. The star. In
So
the end.
other elements is unstable. You mean that?
Yes.
What do you mean stable?
Stable.
Is it because it's a stable isotope, so it's stable? Alright, you can now explain in Chinese.
就最后它会达到一个稳定的高峰，就是有那张表吗？这有一个图，然后它是这样子，然后它贴在这里，稳定。
What is the x-axis? What is the y-axis? Alright?
Yeah, got it.
Do you have something to? Do you have your own answer to your own question, or that is a real question?
And I have to find some information, and I find that some elements that heavier than iron will be destroyed or something. I'm not really memorized with that, but I think that a lot of elements that heavier than iron was creatured after the supernova. I'm certainly concerned about that.
Alright, I thought your question is why is the at the end of at the final stage of a big star, why is the core iron? I thought that was your question. Is that your question? At the end of at the final stage of a star, why is the core made of iron? I thought that was the question. And you try to answer with that graph, which is actually right, correct. But you cannot remember what are the axes. So anybody who wants to add on? Okay,
I think it is related to the binding energy. That after the sun is forming iron, and the bigger element is not. The sun can gain the energy through the nuclear fusion, so the sun began to collapse and cause supernova, and as through our process form heavier elements.
Okay, I will add on. That was all correct. I will add on because iron is is the final product of spontaneous, I have to emphasize, spontaneous, 自发性的, spontaneous nuclear fusion. Because during the process of nuclear fusion all the way up to iron, there is always a loss of mass. That's a key point, a loss of mass. However, if you want to create a new nucleus from iron to something like a uranium, there's no loss of iron, no loss of mass. Therefore, there is no spontaneous nuclear fusion. But of course, if you add energy into this process, you can artificially create nuclear fusion, right? Okay, A group student, question, Jackie.
I want to ask, is it possible for our process happen in regular life of the star?
Regular. Did you hear him? Is it possible for the R process to happen in the regular life of a star? Right?
It has to with really great masses, so it will collapse and to explode supernova. To this one explodes. Yes.
Are you satisfied with his answer, or you have something to add on? I think you have something to add on. Chinese?
OK， 就是它那个超新星爆炸才会有那个让它有那么大的能量可以产生 R 过程嘛。
对。
那可是那个在平常恒星在燃烧的时候，它也是一样，就是中子也有自由中子有可能会碰到那个原子核，然后再蜕变变成那个原子序加一。那这个过程就是没有任何一件可能，就是它会产生这样子的方式，让那个铁可以变成铀。
读到应该没有我读到应该是不会的，就是它就是因为爆炸，所以它可以快速的累积，就是它中子会不断撞到那个铁的核心里面，所以它的质量会增加。啊，如果是一般过程的话，它就没有那么巨大的含量，就可以产生像铀这些质量。
My suggestion is that what Jackie was referring to is actually the S process. So we simply call it S process. Of course, neutron capture can happen in the regular life of a star. But in that sense, we will not call it R process because R means rapid. So it's an extremely rapid process. And this is how we define it because it takes place only during the supernova explosion. Okay. A student, lady first, tell us.
So when I'm reading, there is a sentence that to define our process and S process, our process is more neutron rich. Do you read something about neutron rich?
Okay, how do you explain further about neutron rich?
Neutron rich.
Right, isn't S process neutron rich? Why do we only say, oh, okay, the R process is more neutron rich? Why? It says 好难哦，Nobody cannot answer. Can you?
No.
You have something to add on?
But I only searched a few things and it didn't tell details. It only say neutron rich, more large ratio of neutron to proton. And for the figure 3.3, physics, you can see the neutron is, it seems, I just say, I only can say it's more than, the difference of the neutron to proton is more than X%. But I don't know how, they didn't give a specific ratios of neutron to protons. So I don't know.
Okay. Anybody who want to ask on? Okay, Zhi.
Ask on.
Is it a question or you want to answer this question?
Yes, okay. I think it's because the speed of the process. Because in our process it's rapid process, then you will add on the neutron more faster. If more faster, then it can get more neutron before decay. Then for S process is slow process. So add one neutron, then decay become proton plus electron, something like that. So the speed different, then the neutron that the nucleus can get is different.
Okay. Very good.
It means the neutron rate is because of speed.
It's not just because of speed. The speed is just the reason why it's neutron rich. And how do you read neutron rich? It's very easy. Let me see. It's our S process, right? Okay. So let me explain with this graph. Here we define an element based on the number of protons. So these are zinc. This is zinc. And these are its isotopes. You see, zinc has many isotopes. However, neutron rich means, for example, here you see this block. Here it says, stable isotope not produced by S process. Then, which process produced this isotope? You can guess. The answer is R process. So, compared to all these isotopes, this one has the highest number of neutrons. So that means neutron rich. In other words, you can always say, if this is a span of stability, which is the composition of all stable isotopes, then all the isotopes with the highest number of neutrons, like this one, they are mainly produced by R process because they need a lot of neutrons. And for those which get stuck again, okay. For those which do not have that many neutrons, they are mainly produced by the S process. Does that answer your question? Okay. Hang on. Ray.
What do you mean the rapid neutron at the first rate or second?
This one?
I don't think it's this one. Next one. Yes.
Yes, this one. How do you mean rapid neutron and a massive star? Did it have a definition?
Rapid neutron. I don't see rapid neutron, but I know it's somewhere in the slides. And massive star. I guess massive star is easier.
A massive star just we learned about last week. Yes.
And is that your answer?
No. A massive star, and we see the main sequence. Main sequence, and those who has the bigger masses will turn into giant red.
Maybe you can tell us what is the reference compared to what it's a massive star we will say.
Where's the star?
Wow.
It is 10 or more or 25 times mass than sun. When we can call it the massive star.
Rapid neutron.
Rapid neutron.
Is there a definition for that? Is there slow neutron?
Slow neutron. I think rapid neutron because the explosion gives it a lot of energy, so the neutrons reaction is very fast. So
Do you have
it's
something to add on regarding rapid neutron?
very, very fast.
Do you? Like maybe you have a number. How fast is the rapid neutron?
No, but I think it's the gravity and the temperature making move more faster.
Okay.
So if it move faster than the decay, so it becomes as well.
Okay. Well, that's a good point because you know the half-life of neutron, free neutron, is only 10 minutes. So I would say that would be a good point. If it moves extremely fast, hit another nucleus before it decays, maybe we can call it rapid neutron. I myself, I don't know the answer. Okay. Ethan.
Speaking Chinese，我有个数据就是说，rapid neutron 就是每平方公分就是有12次方的自由中子，然后半中子是每平方有10的6次方的自由中子。
Oh, thank you for providing this quantitative definition. Thank you, Ethan. All right. I actually have a question for you because you already you are very honest. You say I copied the text from the textbook. Can you go to slide number 4? Right, and display. Play. Right. Okay. I was actually hoping that you can explain by figure.
Oh, you say one
Yeah,
plus
well,
one.
for example, what I was expecting is, okay, you can tell us, you can tell us what's this, what's that, this, and then how to read this graph. Can you?
I do my best.
All right.
First
You have
off,
to explain all the symbols.
all the symbols. First, first we just start from this one and this one. Okay. And an explosion, so the neutrons get into this nucleus.
Okay.
And another neutron get into the nucleus.
What
And
are the black arrows?
black arrow. This one?
Arrows.
I have black arrows.
Here it says, what
That-
is that?
It's the neutron capture in the R process. So it gets very rapidly. So and in this movement it suddenly stop and it process the beta decay.
Why do you think it stops here? Why?
It stop here. I really don't know.
Because it's saturated. 吃饱了，吃中子吃
Too
到饱。
much.
Yeah.
Yeah, too much. And then it turned into the other heavier element.
Which process?
This process.
Which is called?
Which is called
It's on the screen, right?
beta decay.
What does it say here?
Beta decay.
Right?
Okay. And what's the other detail?
Then what is the difference? This is beta decay.
Yeah.
This is also beta decay. So what's the difference?
The beta decay just during the R process is just in a few seconds. So this is the beta decay. So it eats a lot of neutrons, so it becomes unstable. But after that is not the time for rapid process. So the unstable elements will start to decay, and because it's very unstable.
Alright, so that's a process. And you can see it always creates the stable isotope with the highest number of neutrons based on this graph. It's at the right lower parts of the band of stability. Okay. So I assume that if you can read this, then you can also read the S process. So I will not repeat it. Okay, thank you.
I'm from Team B. Then this is the figure 310. Then you can see I have marked up some questions from the assignment. This graph for the y-axis is relative abundance of nucleus in the sand. Then for the x-axis is particle number.
You might want to try.
Okay. Particle number, neutron plus the proton. Okay, so for alpha particle, what is alpha particle? Alpha particle is for the carbon, oxygen, sodium, and more until the closure. You can see it is a grade of the very stable nucleus, helium nucleus. That means it is all multiple of 4. You can find out 12, 16, 20, all of them are multiple of 4. So it's maybe 1, 2 helium, 3 helium, 4 helium, or 5 helium to a grade to become this alpha particle. So we call that alpha particle is just like a nickname just for this particle. Okay. Then all of them are primary products of the nucleus fire. That means produced in the star. Okay. Then here is the iron peak. Then just now the team A already talked about iron from the sun. Why the universe got the iron and have much abundance of the iron? Because we can see here is a decline, then a peak again for the iron. That is because just now team A has just talked the reason about that. At the end of the nuclear fusion that happened in the star is according to the assembly line. That means in the star we have seen the picture, helium, the iron, then carbon, oxygen, silicon, something like that. Then inside have much of the iron. So we have got an iron peak over here. Okay. Then nuclear cooking. Actually, I didn't find out the actual meaning of the nuclear cooking. But I think it's the nuclear burning or fusion in the core of the star. So it's just from the iron because in the nuclear of the star, in the core of the star that happens to make the nuclear fusion until the last step is the iron. So I think nuclear cooking is equal to nuclear burning or nuclear fusion. Okay, then electron capture. Electron capture is happen during the explosion that marks the death of a massive star.
Sorry, I
it's okay. A host of the nuclear reaction occur that release free neutron. Okay, that means during the death of the massive star that bigger than the sun much more, then it happen explosion, then release a lot of neutron, free neutron, didn't decay, have not decayed. Then the neutron have no charge and can just collapse with the nucleus, freely enter because it did not have charge, then will not happen the repel. Then the iron atom at the last step of the core of the star, it will hit by the neutron and hit by neutron while the fast speed and the explosion in high heat and all. Then until it cannot absorb any more of the neutron, then it will undergo the beta decay by emitting an electron and become proton again, one proton again, and have the higher massive of the element. Then nuclear reaction occurring during this explosion create elements heavier than iron. Okay, then we call this process neutron capture. Okay. Okay, this figure is the 3-1 relative abundance of the element in our sun. Then for the x-axis is atomic number, for the y-axis is solar system abundance. Okay, it's such same with the first graph. The first graph is the abundance of the universe, but I don't know why the y-axis is right. The y-axis is right in the sun, but something is different, I think. Okay. Oh, the scale is different. Just now the graph is just much bigger scale. Then this is the zoom out scale. Actually, it's a stem graph. Okay. The relative abundance of the elements is the number of the atom of the element for each 1 million atom of silicon. Then you can find out the x-axis. The silicon over there is 10 with the 0. No.
10 to the 6.
10 to the 6 silicon. That is 1 million, right? Okay, so it depends on this as a index, not index. Reference, okay. Then they draw up all the element abundance. Then why they can know the elements is from the solar spectrum that we have learned before in the class. Okay. Then how are the following elements in the sun generated? For beryllium, this is my own answer. Actually, I'm not sure for the answer is correct or not. Okay. The beryllium is from the collision in the first day of the Big Bang. Actually, the Big Bang of the first day, it will produce a lot of hydrogen and the helium. Then, in a very small very small 机会
Probability.
Yes. In a very small probability, the beryllium will occur, lithium, beryllium, even carbon, but it is very small probability. Okay, so we can see that the beryllium in the graph is also in a very small amount. Okay, then it's oxygen. Oxygen, I think it is made by the oxygen core in the middle or massive star. Okay, not in sun. Sun cannot make oxygen, but in the middle or even more massive star, it will have a oxygen burning core. So the oxygen is come from here. And the next one is thorium. Thorium, I think, is from the R process. Thorium is with the 90 atomic number. So from in the R process, the rapid addition of the neutron during supernova, that means the massive star has exploded. Then they happen the neutron capture, then become in a fast speed and produce most neutron nuclide like thorium. Then all of these elements will find in the sun is because the sun is a lab from. Sun didn't make the element, but others make the element. Some bigger, massive stars have exploded in the much further time. Then in the universe, the sun is formed lately. So the sun will bind out with those elements in the universe before it become today we saw the sun is just like this. Okay. So element has been enhanced by the explosive death of large number of red giants that formed and died in our galaxy long before the sun formed. Okay, that's our assessment.
Okay. Group B students, Ethan.
Why you say the sun cannot produce oxygen?
It is because the sun is. I said that cannot process is inside the sun. The sun is from the helium and the hydrogen burning core, but it don't have the oxygen burning core. If more massive star, then it can make it, but our sun is too small.
That's right. Question from Group B students? Any? Everybody's satisfied? Okay, Vincent.
Can you turn the thing earlier? Number 2. And number 4, sorry. Can you explain why in the figure lab some elements that didn't appear just like the harmonic number for around 40, around 60, and around 90. Some elements didn't appear here.
I didn't find out these questions, but I think that is because some element is such the stable isotope is very small amount. Then when the sun is formed, the probability to get the element is much more harder. So then it can happen if some element didn't find out in the sun.
Do you have your own answer to this question?
I remember when I read the material, it said there are some, in fact, it writes something on the figure because those elements didn't appear yet. It's very unstable. So when it forms, it quickly decays, and so it can be it can stay in the solar system. So the element exists, but it decays very fast. So now we can find it.
Right, so let's talk about radioactivity of the elements. Any question from, okay, great.
Alpha particle is the definition is the mass is 10 to 40. So why is the mass is 44 is not an alpha particle?
Wow, that's a picky question, right?
I think it is just want to do a separate with the nucleus that is more than 40 atomic number, because those alpha particles will find out in the core of the massive star. Then they will have a much more abundant number. So if 44 is just have less amount in the abundance, so they are not care about it. All of the alpha particle is in a large abundance. So if we just call it a nickname, then you can know that alpha particle is a much abundance in the universe.
You have your own answer to that?
No, plus.
Okay. I myself, I don't know the answer. So, you know? Alright.
I'm not sure, but this is figure 310, and in the context below it stated in the mass range 10 to 100, nucleus with particle number divided by 4 have an abundance for above those of their neighbors. So I'm not sure, but I think if, in my understanding, it means mass range 10 to 100 and divided by 4 is all alpha particle. So all particles here, just like 12, 16, and maybe 18 is all alpha particle, but I'm not sure. I just read the content here.
Okay, that might make sense. If it says only up to mass 100, right? Okay, then there might be a cutoff for the mass 44. So, all right. Any more questions? Comments? No? Okay. Zhiying, thank you. We have talked about this very small star, low mass star. Definition is less than half of the solar mass. And we will say it's completely convective, it's only doing the hydrogen burning to helium and die quietly. And then we talk about the sun. We talk about the sun, and then the key point is I explain why a giant will take place, will be formed at a later stage of the sun. This is because of the shell burning stage. That was from last week. And then I tell you, right, shell burning. And that's the relative size of the star, of the sun. And then I tell you why planetary nebula can be formed when the sun is about to die. So if you throw away all its clothes, it will be like that. So that is a planetary nebula. And then when the sun is about to die, it will form a white dwarf. Okay, that's from last week. And then let's review this term. At the end, the nuclear fusion will stop, and then the material will start to collapse again. However, because of the small mass and the low, because of the small mass, then it does not exceed physical limit called Chandrasekhar limit. Therefore, when the material collapses, it will not exceed the so-called electron degeneracy pressure, which means the electron is forced to enter the nucleus during the collapse of the material. In that sense, the material is not as you understand. It's a totally different kinds of material that you will not see on the Earth. Okay, and this will happen only when the electron degeneracy pressure is exceeded. Okay, so let's remember this term. Alright, so now we will talk about the last part, which is the massive star. And here we say the definition is more than 10 times of the solar mass. It will lose their mass very rapidly in order to create sufficient radiation pressure against gravity. So there's a lot of potential energy, pressure from the potential energy, so it will burn rapidly, and it will form an onion-like structure as Zhi Ying talked about. And then during shell burning, they tend to stripe off their own envelopes, their clothes. Okay, we call it envelopes. So it's a little bit like an outer atmosphere of the sun, and exposing the deeper layer which have higher temperature. Therefore, you will see blue giants. In other sense, it's a little bit like planetary nebula. So the star is throwing away its clothes and expose the internal hot core. So it will look brighter and hotter. So it turns blue, right? And once they exhaust, they use up their fuel. As the mass exceeds the Chandrasekhar limit, which I talked about in previous slides, a catastrophic implosion occurs. The term implosion means explode inward. 内爆, okay? Not explosion. Explosion means push outward. So, implosion. Here is a cartoon. Oh, I don't have the cartoon. Sorry. Later. During the implosion, so inward explosion, electron capture will occur, which means because the mass is so large, electron degeneracy, 电子简并, okay, it can take place because of the large mass. In that sense, electron is forced to enter the nucleus, and in that sense, it will the so-called electron capture, as you learned from the first class, will happen. Then it will produce neutron. So, electron plus proton, E plus P will be N. So it will produce neutron. and other particles at the core. And infinite, 无限的 infinite collapse is halted, stopped by neutron degeneracy pressure. So now you see there are two kinds of degeneracy pressure, the electron degeneracy pressure and neutron degeneracy pressure, which means the neutron, they resist to turn into other kinds of material. Because now all electron is forced into the nucleus, so now the nucleus is made of neutrons. And collapse of outer material onto the dense degenerate matter, which is all made of neutron, in the core causes rebound. So what is rebound? This is rebound, bounce back. So something falls and bounce back. Rebound. And the rebound will produce shock wave. During the rebounds, will accelerate outer material, forming a supernova explosion. So the supernova explosion was actually first implosion and then explosion. The degenerate remnants, so remnants is 残余物质, okay, are so-called neutron stars, 中子星. So neutron stars are made of neutrons. So supernova explosion is important for element redistribution and important for our topic next week, which is planetary systems. Because so far we are talking about only stars. We did not talk about planets. But actually supernova explosion is important for planets, not only for heavier elements. Alright, this is a graphical demonstration how this works. So at the beginning there's an onion-like structure for massive stars. And at the end of this slide, because all the fuel is used up, it will implode. And then electron capture will happen to form a lot of neutrons at the center. And when a lot of neutron accumulates at the center, this kind of degenerate matter is extremely solid. When additional material continue to collapse on the core, they will bounce back. So we call it rebound, due to collapse onto degenerate matter. And then there will be shock waves. And at the end you will see the supernova explosion. And this is an example. This one has been documented in ancient China historian or something. Crab nebula. Alright, at the end, supermassive star with more than 3 solar mass. At the end, neutron degeneracy pressure is not enough, insufficient to stop the collapse. In physics, they say the collapse already exceeds the Thoma-Oppenheimer Volkoff limit. Alright, it's just another term. You just remember the gravity is so high. In this place, the infinite implosion, you learn the word, will continue, will go on and go on and go on until a black hole forms. So you see there's a continuum of different level of implosion, and at the end, a black hole will form. And as some of the astronomy lover might notice, last year in April, human, for the first time, captured the image of a real black hole. Donuts. Okay. And yeah, that's something new, right? Alright, so I will skip this one. It's just a graphical summary of small stars to large stars. All right, so now we have finished stellar evolution and nucleosynthesis in stars. Hi.
May I have a question about the black hole?
I'm not sure if I can answer you.
I'm very curious about that. All element, which is the velocity is slower than the sunlight, will be abstract by black hole. What about the element that abstract after the black hole? I mean, according to physics, some 就是你的东西被吸进去了，它吸进去，然后呢，它物质就是怎么讲，它不灭进去啊，对啊。
To answer you, I recommend you to watch the movie Interstellar. No one knows. 星际效应你可以看一下。I don't know, and I guess most people do not know what happened because it is very difficult to make observation of the black hole because nothing can, very little thing can escape. Later in the video, you will see how scientists talk about the observation about black hole. All right. And then you already know about neutron capture. I will skip this. I will skip this one too. Oh, during the break, Pin-Zhen asked, is this stable isotope? No. This is not stable isotope. This is neither stable. This one looks like band of stability, but it's not. It looks like band of stability because, as Kevin said, the S process, the nucleus will closely follow the track of band of stability because it's a slow process. So it will follow the track closely. But these are all mostly radioisotopes. And these are radioisotopes. Thank you. All right, R process, skip. Okay, then S process, skip. Consequence, Zhiying already discussed this, so skip, skip. All right, I will skip this one. That's something Kevin has wanted to say, right? All right, let's watch again. Mass number in x-axis and binding energy in y-axis.